On to page 2. Here we go with the stoichiometry mole to mole. This means you're starting with moles and solving for moles of something else. Now we have this example here, this generic example. A chemical equation where you have 2 parts A plus 3 parts B will create 1 part C and 4 parts D. Those are just fake elements with fake coefficients. Trust. This fence post method here is just like using the fractions. Sometimes it's easier to just draw a line and then separate that one solid fraction bar with a bunch of posts. Or if you wanted to, it would mean the same thing if you did 5 moles of A over 1 times 4 moles of D over 2 moles of A. It's the same exact math. 5 times 4 is 20, divided by 2 is 10, and then moles of A cancels out, leaving you with moles of D. It's the same stuff. I just wanted to make that very clear. Sometimes you'll see my answer keys or work written as the fence posts, and sometimes you'll see it written as fractions, but it all means the same thing. Let's do some practice here with mole-to-mole calculations. Start with 6.2 moles of HCl. How many moles of hydrogen form? Well, you can't do anything until this equation is balanced, right? Let's see here. I have 1 magnesium, 1 hydrogen, 2 hydrogen, 1 chlorine, 2 chlorine. If I put a 2 here, now I've got a balanced equation, 1, 2, 1, 1. And this is the same equation right here, 1, 2, 1, 1. 6.2 moles of hydrogen, here we go. Or excuse me, 6.2 moles of HCl. How much hydrogen did I form? Well, moles of HCl go in the denominator, and moles of H2 go in the numerator. For every 2 moles of HCl that I use, I will make 1 mole of hydrogen. So 6.2 times 1 is 6.2, divided by 2 is 3.1. Moles of HCl cancels out, leaving me with 3.1 moles of hydrogen. Pretty simple. Then, 2.4 moles of magnesium. How many moles of hydrogen will form? Same exact kind of calculation. Moles of magnesium go in the denominator. Moles of H2 go in the numerator. I want to have those units matching so that I can cancel them out later. For every 1 mole of magnesium, I will use 1 or make 1 mole of hydrogen. 2.4 times 1 divided by 1 is 2.4. Moles of magnesium will cancel out because they are in the numerator and denominator, leaving me with moles of hydrogen. Pretty cool. Next example, you form 3.5 moles of aluminum oxide. How many moles of oxygen are used? Well, I have an odd number of oxygens here, so I'm going to make it even, giving us 6. 3 times 2 is also 6, and then 2 times 2 is 4 there, so that's going to give me 4 aluminums here. Same equation, 4, 3, 2. Go. So here we go. 3.5 moles of aluminum oxide were produced. How many moles of oxygen were used? Well, same unit in the denominator of the next term, Al2O3, moles of Al2O3, and then moles of oxygen in the numerator. For every 2 moles of aluminum oxide that I produce, I must use 3 moles of oxygen. So 3.5 times 3 divided by 2. 3.5 times 3 gives me 10.5 divided by 2. You're looking at 5.25 moles of O2. Bang. Then you form 3.5 moles of aluminum oxide. Let's see. Which is the same amount that we formed in the previous question. But now we're solving for the other reactant. Are we allowed to do that? You bet we're allowed to do that. Why wouldn't we be allowed to do that? It's not like it's off limits, unless it is. That would be kind of crazy if I was recording a video about that, if it was off limits. Now, same units, great. Numbers come from the coefficients in the equation to give me this mole ratio. And here we go. 3.5 times 4 is 14? Hey, how about that? Divided by 2? 7 moles of aluminum oxide cancels out, giving you 7 moles of aluminum as your answer. So that means for every 3.5 moles of aluminum oxide that I make, I will use 7 moles of aluminum. It's that simple, guys. Really, it's that simple. Stay tuned for part 3 where we go over grams and moles.